Okay, friends, I think we will get started, right? Before I get started, recently I read something and I want to share with you before I get started, right? See, in your hand, there is a lot of acupuncture pressure points. And when you clap like this, all those pressure points gets activated, and the person who is going to be who's clapping is going to be feeling very relaxed, right? Because when you clap, all those acupuncture pressure point gets activated and blood flows really well, and it's very relaxing for you, for whoever is clapping. So all throughout the session, feel free to clap whenever you wanted to, right? Right? Maybe we can clap once now. Okay. So thank you. I think now the other rooms might think maybe I should attend this session. It got over so soon. Okay. Okay. We will get started, right? Top 5 Java performance problems, right? So what we are going to be learning in this session, right? We are going to be obviously discussing some of the very common Java performance problems, and we are going to learn with real case studies, right? These performance problems happen in real enterprises, very major enterprises, and I got the real data with which they troubleshooted these problems, and we are going to be looking at it in this session, right? And also, we are going to be learning very efficient way to troubleshoot and diagnose these problems. So that's what we are going to be doing. Okay. One of the common problem is your backend slowing down. That is, say your application connects with several backend system of record. And if that backend system of record slows down, it's going to impact our applications, right? So this happened in a very major financial institution in North America. So I'm coming from California. So this financial institution products and services is used in 1 in 3 households. It's a very major financial institution. So this had an unresponsiveness in their application, right? So let's see what we did to get to the root cause of this one. Friends, before even getting in there, let's talk about a typical application architecture, right? So this is a typical application architecture for most of the applications, whether let it be a web application, mobile application, serverless, most of them follow to this convention. There are outliers, but predominantly this is what the architecture is, right? So say a new request comes to your application. Your application has an application server. It has an application server. And the very forefront, we do have a server thread pool, right? And at the backend system of records, at the backend, your application talks with, see, actually, because of a lighting, here there is a gray box. This gray box is totally missing. But here there is this gray box, which is acting as application server. Maybe because of lighting, it is not showing up, but visualize, there is this application server, right? So at the back end, there is a different system of records to which your application connects with, right? It could be running from REST-based applications, SOAP, JDBC, all the way to mainframe. So when a new request comes, this server thread from the server thread pool picks up that request, and then it goes, and then it makes a call to this backend REST system, right? And this backend system is going to give you back a response. Once this response is given, then this thread processes the data, massages the data, and then gives back the result. Once it gives back, the thread once again goes back to this thread pool, right? So this is a typical architecture in most applications. Now, let's envision a scenario where this backend system is having a slowdown, right? Typically, this backend system of record gives us a response in 100 milliseconds, say it is having some outage. So it is responding very slowly. It's taking like a 5 seconds, 10 seconds, 20 seconds kind of response time to give back the responses. Now, let's say now a request comes. A thread is going to pick up this request, and then it's going to go and make a call. What if the system of record, which is having some outage, it's now starting to respond very slowly? Then this thread is going to be starting to stuck there, right? Typically, it comes back to 100 milliseconds. Now it's going to take whatever the time is, 5 seconds, 6 seconds is going to take. So assume now the requests are starting to come in. So new request comes, a thread goes, it picks up, it's also going to get stuck. Another request comes, this thread goes, gets stuck. Another request comes, goes, it gets stuck. Now that means now what? There is no more threads to process. Or when you create a lot of threads, you're going to get out of memory error, unable to create new native threads, right? That is another problem you may encounter. When this happens, this is one of the very common problem, right? So let's see how to diagnose this kind of problem, right? So to diagnose these kind of problems, see, one thing what you want to do is, when you get a performance problem or a production problem, we don't know what it is. A production performance problem can happen because of different reasons. Maybe there could be a garbage collection pause. There could be a backend slowdown like this. There could be a memory leak. There could be a network issue. There could be a problem with the kernel. It could be anything. So the best thing, what you want to do is, you want to capture a kind of a 360-degree data from the application stack, right? So this is the 360-degree data, right? I want to capture the GC log, thread dump, all the thing. And for this, there is this open source script called as this YC data script. So this script just takes in a process ID as an input. So give the name of the process ID. And when you trigger, it's going to unearth the 360-degree data. And then it's going to, and then once you have the data, then you can go about troubleshooting it, right? So for these kind of issues, right, whenever there's a backend is slowing down, you want to be using the thread dumps to diagnose these sort of issues. The thread dumps are very useful to troubleshoot several problems, but this is very vital. This data is very useful for these kind of problems. You can use the thread dumps, right? How does a thread dump look? Has anyone deal with thread dumps? Oh, I see a lot of hands going on. Very good. I know I'm clapping. Okay. So just for the other folks, right, I'll just give a very quick introduction of what a thread dump is, right? Okay, friends. So this is how, when you take a thread dump, this is how a thread dump typically looks, right? So at the very top, it has the timestamp in which the thread dump was taken. Don't worry if these are not clear. It's not of much importance, right? And the second one is, it shows the timestamp in which, no, the first one is the timestamp. The second one is, it gives the information about the JVM, whether it's a 64-bit JVM or it's a 32-bit JVM, whether it's running on a server mode or a client mode, it's going to report that. The next is, say, suppose if your application has 100 threads, for each thread, this segment is going to be reported. So if you have 100 threads, there is going to be 100 segments reported for each thread. Right? So what is the information within this segment? Let's zoom in to that one segment. What are the information is there? So the first information what is there is the name of your thread. This is the name given by the developer, right? And the next one is the priority. A thread can have a priority from 1 to 10, 10 being the highest priority, right? So when there is any CPU contention, a thread with highest priority gets to run. But it is a recommendation given by the JVM. It's only at the kernel who makes the final decision. And then third is the thread ID. What is thread ID? The thread ID is kind of the ID given to that thread by the JVM. This is the name that is given by the developer. Developers, we know, we can give duplicate names, right? The thread name does not have to be enforced. But this is the ID given by the JVM. And there is a next ID called as native ID. NID means native ID. This is the ID given by the operating system for the same thread. The way you want to visualize this can be, say, the name, my name. It can be my name given by my parents, right? And the thread ID is kind of the ID given by my state government. And NID is kind of the ID given by the federal government, the central government, right? But it's all different IDs pointing to the same thread. And then here is the address space in which the thread is running. And this is the stack trace. That is where the thread originated. This is the very first line the thread executed. And after executing this line, the thread moved on to execute the second line, third line, like this is progress. And finally, when you took a thread dump, this is where it is executing. This is the line of code it is executing, right? With this is all the thread dump contains, nothing more. But with this, you can uncover so many problems, which we are going to look at it right now, right? So now what I will do, to analyze the thread dumps, you can do manually also. You can also manually analyze. But here are some of the tools that I would like to highlight, right? You can use these tools to look into the thread dumps, which is kind of an automated way to look into the problems, right? So now what we will do, we will look into this financial application, which had a slowdown. How does that thread dump looks like, right? That's what we're going to be looking right now. So for this, I'm going to be using the tool called as the Y-Crash. So what will happen? So whenever that incident is reported, it's going to be reported here, and all the data is going to be analyzed. So all the 16 data is going to be analyzed and then going to be presented to you here. Like say here is the thread details, garbage collection, everything is going to be here. But I don't want to be talking about the tooling aspect. You can still do manually also analyze this one. So now let's look at this data, which had this outage, the financial institution, which was used by 1 in 3 households, right? This issue. You can see at the very top, it kind of gives you a warning. I don't know whether you guys are able to see. Let me zoom it a little bit bigger, right? Okay. See here it says, this application is having like 1,859 threads. Typically, this application has only like a 300 or a 400 threads. This itself is a flags warning. It is having like a 4 or 5 times more threads than the normal time what it is. Now, coming down, look at this. There are multiple sections, but here there is a section called threads with identical stack trace. What this section does is, it groups the threads which have identical stack trace, and then it presents its size. Here you can see, out of those 1,800 plus threads, 1,700 threads, which is almost more than 95% of the threads, having this exact same stack trace. There is more than 95% of the threads is having exact same stack trace. When you analyze the thread dumps, you want to look for the group them, and you want to see if multiple threads exhibit the same stack trace, that means there is some problem is going on in that stack trace. Imagine like if the backend is slowing down, all the threads are going to be getting stuck here. So here it says, it gives you kind of the helpful warning. Let's go and look at the stack trace. Here is the stack trace. Here you can see, this is originating from the package called as Oracle. This was actually talking to an Oracle database. This middleware platform was talking to Oracle database. And you can see since this was a middleware platform. So the Oracle, the database vendor, it was one of the primary system of record this financial institution was talking to. The Oracle, the database vendor, told you enable the flag called ONS, that is online notification service. Here you can say ONS on the JDBC driver. When you set it to true, what will happen is, what the promise they gave us, you're talking to an Oracle RAC cluster. It is a multi-node cluster. Even if one node in the cluster goes down, when you set this flag to be true, automatically the next available node will start to take the transaction. So its availability will start to go higher. So that's what they recommended. So this team also enabled that flag to be true. But once enabled to true, there was a bug in the JDBC driver, due to which the threads started to leak. So any thread that goes, for any request that came, a new thread was spawned. It was going to database and it was stuck there. So the thread started to build up. When it started to build up, this application was kind of becoming unresponsive. The moment they took the stack trace and showing there are like a 95% of the threads are stuck here, then the Oracle acknowledged, okay, this is a problem. And then they made a patch. Once the patch was installed, then the problem went away, right? So this is one efficient way to look at the problems, right? Now let's move on to the second problem, which is garbage collection. Okay. See, friends, this problem happened in a very critical service of a very major cloud provider. When I say cloud provider, think about top 3. This is one of the cloud provider. And this is very critical service, right? Let's look into the problem, what they ran with the garbage collection, right? First of all, First of all, what is garbage? Does anyone want to say? What is garbage? Stuff that you don't need anymore. Okay, very good. That's right. Anyone else wants to say anything? Any context it can be. In the context of JVM, maybe. Unreferenced objects. Yeah, very good. Right. So what is garbage? Some people say my talk is garbage. Right? Yes. Yeah. True. Very true. So, friends, look at this. Okay, thank God I have this gray now showing up here. Okay. So, friends, all application or memory is a finite resource. Our memory is a very finite resource. So let's say a new HTTP request comes in, right? Let's say it could be a sign-on request. To service a simple request in modern days, we are creating tons of objects. We are creating thousands of objects just to service a simple sign-on request, right? If you're running on a Spring Boot, Spring has its own objects, and it's creating a servlet request object, a customer object, and then customer object has username, password, and then we're creating a DAOs, a connection object. We are making a backend call. It's coming back with the result set, which has multiple things. So many objects are getting created. So we create all these objects. And now we service the request. Once the request goes away, these objects, right? There's no more reference. This got created, it's serviced, and now these objects becomes garbage. Right? It's no longer readed, and it's a finite space. So your memory has to be reclaimed, these objects has to be removed so that the new objects can be created and you can service the new incoming request. So how is this garbage evicted? How is this garbage evicted, removed from the memory, right? There is an evolution happened in garbage collection 3-4 decades before, right? Before some of you were born, right? As a developer was responsible for writing a code to remove the objects from memory. Once I say new, we all only do new right now. We don't worry about removing those objects. But 3-4 decades back, as a developer, you need to write code to remove these objects from memory. Right? They have to do. But there was a couple of challenges with that. One is the business case is pretty complicated, right? Our business application is pretty complex. And even if a developer misses to write removing the object from one single use case, then the object will start to grow, the memory leak would happen, and the application would crash. When Java came in 1995, it promised, hello developers, you don't worry about removing the objects from memory. It is my responsibility to remove the object from memory. I will automatically find what are the unreferenced objects. Then I will remove it from the memory. So that's what it started doing. Since then, even there were languages before Java, it was doing it. But Java really took it to the mainstream. And then since then, all the new language that is coming in, they're doing automatic garbage collection, right? Which is the right thing to do. I don't disagree. Totally, it is the right thing to do. But this has a couple of side effects. This garbage collection, automatic garbage collection, has a couple of side effects. What is the first side effect? When garbage collection run, it pauses your application. Your application stops. That is the first side which you're going to look right now. And the second side effect is it's going to consume enormous amount of CPU. A lot of friends doesn't know. If your application CPU consumption is like a 60%, probably more than 30-40% is taken by garbage collection, right? So I'll talk about these details right away, right? So to troubleshoot these kind of garbage collection issues, which that major cloud provider was suffering from, you want to use the garbage collection log, which is given here, which is captured by the script, right? So let's look at the actual garbage collection log of the cloud provider, the critical service of the cloud provider. Let's look at it. And here are some of the tools that you can use for analyzing the garbage collection log, right? I've put some of the tools here. So now let's go. Friends, this is the garbage collection log of that cloud provider, the real cloud provider. You can see it is reporting like 244 events are taking more than 5 seconds. That is when the garbage collection ran, like 244 events took more than 5 seconds to complete. Now let's come here. Like it gives you all the recommendations, but this is the most interesting section. You can see the average pause time was 12 seconds. That is when a garbage collection event run, it is pausing for 12 seconds. If I pause for 12 seconds now, some of you will sleep, but I can see some of you are already sleeping. But okay, that's fine. So, right, think about 12 seconds, friends. How much is 12 seconds? It's a lot. And look here, here is the garbage collection duration. You can see it is continuously pausing for multiple 12 seconds, this application. That means if any request that is going to be coming in, they're not going to get any response back. Because if during the 12 seconds, if anyone is going to get a request, if you're going to send a request, you're not going to get any response back. Think, even our car, which is an electromechanical device. Think about this. If a car, I take a car and I'm driving, what if it stops in the road for 12 seconds in the middle? And then now after that, it starts to run. And then once again, it stops for 12 seconds. How we will feel? Pretty bad, right? But our JVM does this. It's a JVM we don't see. We cannot see a JVM, right? So this is what was happening. It was pretty bad. Now, what we did was, we did a minor GC tuning. A very, very simple change was done. Look. Here, but even before going that, I just want to talk about another metric. Here there is a metric called GC throughput, right? Look at this. It is 96%. What is GC throughput? What does 96% mean? The 96% means, what does GC throughput in general it means? Let's look at it here. GC throughput means, it means the amount of time your application is spending in processing the customer transaction versus amount of time you're spending in processing the garbage collection activity. If someone says my GC throughput is 96%, it means I'm spending 96% of my time in processing the customer transactions and 4% of my time in processing the GC activity. That's what it means actually. How does 96% throughput sound? And how does it actually translate? Look at this. One day has 1,440 minutes. That means 4%. Means 57 minutes per day. That means for 57 minutes per day, this application is stopping. It is freezing. And we are all running our services on top of this critical service. Right? So this is what, it is pretty bad throughput, right? For one day, 1 hour, this application is stopping. Now, when we just made a GC tuning. What we did was, look at this. Earlier, Earlier, the young generation was kind of 50%, that is 14 GB, and the old generation was 50%, that is another 14 GB. We just made this to be, young generation to be 1 GB, allocated more space for the old generation, like 28 GB. When we did this change, look, the throughput became 99%. Phenomenal increase, just a minor JVM argument change. Young generation size. When we did, you started seeing that such a dramatic improvement. And look, the average pause time became 138 milliseconds. Earlier, it was 12 seconds. Right? So once they did, their application, the critical service started to perform a lot better. They were happy. The customers were happy. Right? Okay. So now, yes. Yeah, sir, that's a good question. But that's if you want to answer that, I need a rest of the session or more than that. We'll catch up later, right? Okay. Yes, that's true. It's not. Yes, I totally agree. It's not trivial, but there are some few fundamentals what you can look and do it, right? Okay. Okay. So the third problem is out of memory error. How many of you have faced out of memory error? Yes, good. If someone doesn't raise, that means maybe you guys are okay. No, that's good. Most of you are raising hand. Very, very common friendly error, right? Okay. Friends, actually, you can predict out of memory errors. You can forecast out of memory errors by looking at the garbage collection behavior, right? Let me show you what it is. So this is a garbage collection behavior of a very healthy application. This application is a very healthy application, right? Look what's happening. The requests are coming. The memory is building up. A full garbage collection event ran. And once the full garbage collection event ran, the memory dropped all the way to the bottom. And now once again, the requests start coming up. The memory is building up. A full garbage collection event ran. And memory is dropping all the way to the bottom. I can see this beautiful sawtooth pattern going on. Look at the bottom points, my friends, right? If I put a slope, the slope is going at 0 degrees. That is this black arrow mark. It's going at 0 degrees. See, it's going at 0 degrees. Now, look at this one. So this is an graph of an application which is suffering from an acute memory leak. That is not aggressive, but it is acute. See what's going on. You can see the request is coming. The memory is building up. A full garbage collection event ran. The memory initially dropped to 22 GB. And now the request is coming. The memory is building up, is going. Look what's happening finally here. When this garbage collection event ran, look, it didn't drop to the point where it dropped originally. It is going up. If I put a slope, the slope is this black arrow is going at 15 degrees. And friends, today people are calling this the slope, which is high school mathematical formula, which we all learned, y is equal to mx plus b. Today people are calling this machine learning, right? That's good. We all know machine learning, some aspects. Okay, so here is that going at 15 degrees. This means this application is carrying a time bomb and it can blast anytime. Now, when it blasts, this is how it's going to look. You can see after a point, even though it runs repeatedly, the memory is not coming down at all. And friends, when this happens, when you are here, we get out of memory error only when we reach this ceiling limit. But way ahead, here itself, the garbage collection is starting to tick up. It's going to keep on running, and memory is not reclaiming. If you look at the GC behavior, there are tools, right, which will show. They can tell, they're going to look at these metrics, the garbage collection metrics, and can tell you are going to have an out of memory error pretty soon. And friends, the pretty bad thing is all the APM tools, they generate alerts only when we get here. But we can get to know the problem here itself. And another thing, when you are at the end of red triangle, that red triangle is a full garbage collection event when it runs, your CPU is going to be at a kind of a 99% or 100%. And friends, always remember, you deployed your code to production. You didn't make any code. You didn't make any new release. You didn't make any flag setting changes. No patches. None of them was done. But all of a sudden, the CPU started to spike at 99% and 100%. There's a very high chance you're seeing this behavior. Right? So when this kind of problem happens, this garbage collection log will be helpful to predict the outage. And once the outage happens, you want to use the heap dumps to analyze. The heap dump is a snapshot of your memory, and that can tell where the objects are leaking. So here are some of the tools which you can look at using for analyzing the heap dumps, right? Okay. And so let's move on to the fourth problem, which is the CPU spike, right? Our application, all of a sudden the CPU spikes. Our monitoring tools today tells only the application CPU spike to 90%, 100%. But I want to know which line of code is causing my CPU to spike up, right? That's what we're going to be discussing. And this problem, what happened was, it happened in a very major trading application. Their CPU started to spike up. They didn't know why. And then that's the data which we got and which we're going to looking at, right? So now, to troubleshoot these kind of CPU spike, you want to use the thread dumps, and then you want to use this another thing called as a top-h. Friends, how many of you, I think several of us has used top command, right? Yes, we all have used top command. Yes. But top command has one secret option. Not that many developers know. Today, you guys are going to know. You can pass this one top dash uppercase H and say -P and give the name of your process ID. When you give that, what's going to happen is the top command, like this, when I'm going to issue like this, it's going to show you all the threads that are running within this process and what is the CPU and memory that they are consuming. Say my application may have hundreds of threads. And friends, always when CPU spikes, it's always caused because of threads. My application may have hundreds of threads, but in those hundreds of threads, how am I going to quarantine and find which are the threads which is consuming CPU? Like top dash H -P gives you. That's what it is here. It gives me, here I see the 3 threads, 31306, 31307, they are consuming like a 69%, 65%, 64% CPU. All other threads are consuming only 0% CPU. Right? So with this, I know these are the 3 threads that is consuming CPU. And now we just have to go and look what these 3 threads are doing. What is the code path? The code path, I'm going to be getting it from the thread dump. Friends, why I'm saying this is efficient way to debug these problems. If you see all the data that I'm capturing, it's just a script I'm running, and it's getting all the data from your entire stack. It is this entire script completes under 30 seconds, and it is running outside, unlike all the APM tools. Even the open telemetry, they all are intrusive. They sit within the JVM, intercept every single call, and then also they don't give the depth of the data that we're going to get from this, right? So now we are getting this data, and the thread dump gives us what code stack it is working on. Now let's look at the actual data of that trading application. Okay, so let's look at it here. Here it is. So it reports all the problems. So here, there is a section called CPU consumption by thread, right? This section marries the top dash H data with the thread dump and gives you, okay, this thread, web container 18, it is consuming like a 60.9% of CPU. Just this one thread alone is consuming so much CPU. And here is the code path. When I click here, I can see the code path. You can see this trading application was running on an IBM WebSphere server. You can see it's originating from there. And finally, you can see it was executing this weak, let me make it a little bit bigger. Executing this weak hash map. It was invoking a put operation. Friends, the hash map is not, it's a interview question. Hash map, what is the difference between a hash map and a hash table, right? Hash map is not a thread safe implementation. It's not a thread safe implementation. If multiple threads starts to do a concurrent get or a put operation on that hash map, then the thread will start to go on an infinite loop. Even if one thread starts to go on an infinite loop, then the CPU is going to spike up to very extraneous percentage. That's what was exactly going on here. So here you can see this hash map, a put was called. So it was taking like a 60, it was in concurrent invocation, which is on a non-thread safe data structure. CPU started to spike up. The moment they saw this, yes, sir. Okay, so after seeing this, the fix was to change the data structure to use concurrent hash map. So this is pointing out the problem. The fix is the developer has to switch to concurrent hash map. Once they did it, the problem went away. Okay. So now let's progress. And another primary performance problem is concurrency issues, right? Caused due to racing conditions. There are different type of concurrency issues, but for our discussion, I'm going to be talking about this particular blocked threads, right? Let's look at it. What will cause a thread to go into blocked state, right? Friends, there is a synchronized method in Java, right? There is also lock, right? There's also lock objects, but let's deal with synchronized methods. When a method is synchronized, only one thread will be allowed to go inside that method, right? Yes? Yes? No? Yes. Okay. when a method is synchronized, only one JVM will allow only one thread to go inside. So now let's say a thread 1 comes. If it's a synchronized method, thread 1 is allowed to go in because there's no other threads working at this point in time. Now, let's say another thread T2 comes now. Will it be allowed to go inside the synchronized method? Yes. Only when thread 1 exits, thread 2 will be allowed to go inside. Until then, the thread 2 will be put to the blocked state because it's a contract. What if, say, within this thread, this method get data, we are calling that do something. What if this do something takes very long time to complete? Then for all the time, the thread 2 has to be in a blocked state. What if during the time another thread comes? Another thread comes. Everyone is going to start to wait. And they are going to be in the blocked state. That means if multiple threads start to come in, then they are going to become unresponsive. They're going to get in the blockchain and going to become unresponsive. So this is that problem that happened in a very major travel service provider in North America. So they process like a 70% of North America's overseas ticket reservation. If you're making an airline ticket reservation, very high chance it is going through this platform. Now let's look at the data that what has been captured and how it looks like. So now, friends, let's come here, right? So this is that data. And friends, this is all the script. When you run, it captures the thread dump. Thread dump adds almost zero overhead to your application. No, we are capturing data in a non-intrusive manner. Nothing like we're not going sitting within the JVM and getting data. And even if you're getting with APM tools, telemetry, they all don't look at these kind of data to get to the root cause. So now let's come down. Here, there is this, whenever the threads gets locked, the tool kind of presents you kind of this transitive dependency graph. Here it presents you at a simple English. You can see this method, this class, Java security secure random, next bytes is blocking like 646 threads. 646 threads are getting blocked. Friends, what is the thread? Behind every thread, there is a customer waiting for us, waiting for result. That means at this moment on this JVM, 646 threads, 646 customers are not getting any response. So here is that the transitive dependency graph. See, there is lines that is flowing in from year to year, but you're not seeing it because of this projection, right? Which is fine. Okay. So now let's look at this. So these are all the victims. These are the 646 threads which are being victimized. And this is the culprit guy who acquired the lock and he didn't release it, right? Let's look at one of the victim, right? I'm going to click on him. So here you can see it started out, it is coming along, and now we can see this thread is invoking this method called UUID, random UUID. You can see. Friends, this is an API that Java developers, as Java developers, we use to generate random numbers. This is a synchronized method. A lot of us doesn't know this is a synchronized method. And you can see it is trying to obtain the lock. The lock is not released, so it's going to the blocked state. It's going to the blocked state. Right? And now, let's click on some other thread and another victim of the 646 threads. It's also coming. It's also trying to invoke this random UUID. It didn't get the lock, so it's also going to the blocked state. So this is the thread, the culprit thread, which acquired the lock and didn't release. Let's click on him and see what's going on. You can see the thread started out. See, it is invoking this random UUID. Right? You guys can see. It's invoking this random UUID. It acquired the lock. See, you can see it acquired the lock. But after acquiring the lock, what happens, friends? When you try to generate this random UUID, the JVM does not generate the random number for us. It delegates the call to the underlying operating system to generate a random number. In the kernel, there is a concept called entropy. What is entropy? To generate random numbers, kernel needs certain signals, certain noises. like noises made by the device drivers. If it's a laptop, it needs mouse movements, the keyboard strokes. It needs those to generate random numbers. If there's a lack of entropy, then the random number generation is going to slow down. That's what was happening in this machine. And this was running on a Red Hat Linux version, which was slightly older version. So then once they did a patch, the kernel patch, then the problem went away. But you can get a sense of this kind of a concurrency issues. Okay, friends, now we have spoken about so far 5 issues pertaining to Java, but I want to be talking about one more issue, which is a kind of a bonus issue maybe. A lot of times this is caused, our outage can happen because of some environmental reasons. My application may be totally fine, but it could be some of the noises coming out outside. I can have an outage. So this problem, this application, what we are talking, it was suffering from HTTP 502 errors. That too, it was suffering intermittently, not always, but intermittently it was suffering from 502 errors. And this application was running on AWS Elastic Beanstalk service. It's EBS is kind of a containerization service. It's kind of a container service. So the application running on it was getting like 502 errors intermittently. They didn't know why. So now, this is the kind of very high-level EBS architecture, the Elastic Beanstalk architecture. At the very top, there is this Elastic Load Balancer. AWS Elastic Load Balancer is there. And then it can have multiple EC2 instances. Within each EC2 instance, they have this Nginx web server, and then they have this Tomcat application server. This is how it was. This is the architecture of EBS. And the application was getting intermittently, it was getting this 502 error. They didn't know why. And this is that error they were getting. Friends, apparently, getting this 360-degree data saved the problem because it was not reported anywhere. One command that the script issues and gets you a dmessage, which is basically, dmessage is basically nothing but a kernel logs. It's a kernel log. It gets to see what are the information reported by kernel log. What was going on? Kernel can sometimes kill your Java application. Several of you might know, but kernel can sometimes kill your application. So when it gets when it kills, it's not reported anywhere, but only it's reported in the kernel logs. Here you can see, here it is reporting that the arrow mark is highlighting. It is killing the process, the Java process. The kernel was actually killing the Java process because of lack of RAM capacity. But why then it should always get always it should get 502 error? Why it is intermittent? Why sometimes it is getting 502 errors and sometimes it was getting successful response? It was because it was a EBS service. The kernel was killing the Java process. But the container orchestrator, it saw the process to be down, it was bringing that up. So kernel was killing, the container orchestrator was bringing the Java up. So when it's up, it was responding. When kernel killed, it was getting 502 error. So application was going up and down, up and down, up and down. So this kind of thing happened. So friends, like kind of capturing this kind of a 360-degree data and looking at it will help us to get to the root cause of the problem pretty efficiently. Okay. So friends, I have a good news now. My talk has come to an end. Right? So thank you everyone for staying here and attending this one. Okay. So I'm here to take any questions. If not, we can wrap up the call. Thank you. Yeah. Yes, sir. Go ahead. Sir, can you be a little louder actually? Yeah. Yes. Yes. So this is a good marketing question. Yes, asked for my tool. So, so actually, I will use this platform, right? I'm not pitching since he asked. I'm talking. So, friends, what is it is, we have this kind of, what we do is, we look at micrometrics. All the APM tools today look at the macrometrics, which are more the reactive indicators. Oh, they look at the CPU, response time, and then the memory. Only they were reactive indicators. Only after a problem happens, I'm going to be reported. But there are micrometrics, my friends. There are micrometrics which can predict outages, which can forecast the problems. One thing that I show the graph, right? Let me show you one more very interesting metric here. Look, there is a metric called average creation rate. How much objects am I creating in a unit of time? I'm creating like a 35 megabytes per second. What if in your previous code commit, you're only creating 10 megabytes per second? Who is looking at this metric today? In your previous code commit, you are creating only 10 megabytes per second. Run a performance test, get this data, and see, oh, okay, it has shot up. Now it has gone up. That means the developer has checked in some inefficient code. This inefficient code is manifesting this higher object creation rate. In production, this is what going to cause as a memory leak or the CPU spike. If you look at the macrometrics, it's going to report whatever the XMX you are configured, or 2 GB, 4 GB, that's what it's going to report. Go down, look into the micrometrics, you can find the answers. Like this, we look at various micrometrics, continuously look at the background, and then we can tell, okay, this is what the problem going on, right? Yeah. So, but we can catch very early. Shift left, truly can do a shift left with this kind of micrometrics monitoring during the development time frame. Any other questions from anyone? So the answer to that was, we reduced the young generation size. The earlier the young generation size was, the overall heap size was 30 gig. The young generation size was 15 GB and the old generation size was 15 GB. That's how they configured. We made the young generation size as 1 GB. Once we did that, then the problem went away. See, this is just for that application that worked. But if you do that, it can be a counterproductive one, right? So I'm doing a workshop on Friday here, right? So there we are going talking about this GC tuning as the things I do. And if not, if you're taking, you're welcome to attend that. That will give you a little bit more insights on how to do this GC tuning, right? That will be pretty good. Or if not, we do also have an online training program here. You can enroll here. You can get into the, we discuss how to do this kind of tuning exercises there. Okay. Yeah. Sorry, sir. Would you mind? I'm not hearing. Yeah. Correct. Yes. 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 No, it needed for the workload to process. It was requiring that. Yes. But reducing the heap size, if you can do, that is one very great thing, because the smaller the heap size, smaller the pause times. See, and friend, this is a good point. Today, my developer says my XMX, the heap size is 10 GB. We always think that 10 GB is the right thing. We are afraid to question that. Whether the 10 GB is the right thing, this is over allocated. Lot of times it is over allocated. When you do the GC behavior, GC study, that will tell you whether you're over allocated or under allocated. Yes, garbage collection study at a point in time is a wrong thing to do, in my opinion. You have to study for a longer period, at least minimum of 1 day, so that your application will see a high tide and a low tide also, right? It has to be done for a longer duration. Yes. Any other questions? Okay, then we'll disperse. Thank you, guys. Thank you, gentlemen, ladies.